Okay. So as I was saying, we've looked at hardness of problems, right? Now, there are two things to do. One is give up. So these are too hard to solve. And the other is like come up with some trade-off, right? So maybe if we ask you to find the vertex cover, right? The minimum vertex cover is good, but maybe you can do some compromise. Maybe you get a vertex cover that has a bit lower quality, but you can get it fast, right? And that might still serve your purpose, right? Think of an application of vertex cover. We saw that we want to maybe place some cameras in certain locations that cover the entire area, right? If you cannot do the most optimal one, you can maybe still do like twice as optimal, and that might still give you a lot of cost benefits, right? A lot of usefulness. So there are many different ways to deal with hard problems, and we'll talk about some of them. But before going into that, what I want to first cover is another very powerful paradigm for algorithms, right? So today's topic is going to be that paradigm, which is called linear programming. And applications, especially applications to approximate algorithms. Okay, so in class, in the first part of the class, when we looked at tractable algorithms, we saw that like there were three main paradigms, right? We had greedy, we had divide and conquer, and we had dynamic programming, right? Greedy is very customized. Like there are only a few problems for which you have good greedy algorithms. The underlying theory is very difficult. It's a theory called matroids. That structure is extremely difficult. So you only end up with a few special cases where you have a correct greedy algorithm, right? And then you get divide and conquer, which also is kind of special. Like there are also kind of limited cases where you have a divide and conquer algorithm. And they're some of them are kind of hard, like FFT, right? But it's a good paradigm. But dynamic programming is very general, right? Whenever you have a problem where you have a recursive structure, you have kind of a fixed recipe of kind of using dynamic programming, right? You kind of find the recurrence relation, find the subproblems, find an ordering of the subproblems, right? Which results in a DAG, and then you kind of sort that DAG and solve the problems in that order, and you have your algorithm, right? And correctness proof is also very easy. And you get good time complexity in general, right? So turns out that, and then the other thing that we discussed when we talk about max flow is that max flow doesn't really have a DP solution, right? But you'll see that max flow actually is intimately tied to linear programming, right? And there are a bunch of other problems, including some of the NP-hard problems, which you can kind of, in some sense, approximate with a linear program, and then solve the linear program, and you get an approximate solution with some performance guarantees, right? So it's a very powerful technique. And then the most surprising and interesting thing is going to be using linear programming, we can actually recover the max flow min cut duality. So max flow min cut is nothing surprising. It's basically when you have a linear program, the recipe is that for a linear program, you can find a dual program, right? And then the optimal solution for the linear program and the dual are the same. And then basically what happens is max flow becomes a linear program, and you take the dual, and that dual turns out to be the min cut problem. And the max flow optimal and the min cut optimal are exactly the same. So that's called strong duality, and we'll kind of look at that. So that's a very surprising and beautiful connection. Right, and in general, linear programming is one of the top 10 algorithms. So we won't cover kind of the numerical algorithm for linear programming, the most popular one being simplex, but we'll kind of understand how to formulate linear programs and how to understand and kind of solve them. Okay. So that was a long introduction to what we are supposed to do. So now let's actually start doing some work, right? So let's use a kind of an example. Start with an example of linear programming. So let's say our application is like someone wants to someone likes baking, like my wife. Like she loves to bake stuff. But then, just like any economic activity, we face choices and we have budget constraints, right? So let's say that, and then when we are kind of building a business, our objective is to maximize profit. Like we want to make money out of what we're doing. We kind of bake stuff or cook stuff, manufacture stuff, and we sell them. We want to make profit, right? So that's kind of the framework of economics, right? So let's say we have a simplified problem where you are a bakery, you have a bakery and you have only two choices. You can either bake a cake, right? Either bake a cake or you bake a cookie. Okay, so simplified, but in real world it's going to be much more complex, but it's a simplified scenario, right? And then the next assumption is we only have two ingredients and we have to make them with two ingredients, which is not true obviously, but we are making a simplified assumption. So the two ingredients are flour, and sugar. Somehow you have to bake with only these two ingredients. I don't know how it would happen, right? So what information do we have? So the information that we have is, so if you make a cake, then you're gonna sell it with a certain amount of money. So let's say it's you sell it for $5. Okay, somehow that's the price. So you can sell cake for $5 per unit. Every cake is $5, right? And then somehow your cookie you sell for, let's say, $2. Okay, I think in the inflationary economy probably it's not true, but let's assume that the cake is a bit more expensive, but these prices are probably not accurate. Okay, and the other information that we have is how much of each ingredient we need for each item, right? So for example, let's say the cake, for one cake, I need 2 units of flour and 3 units of sugar, right? This could be like a spoonful of sugar, 3 spoons of sugar. And then I have for a cookie, I need 1 unit of flour and 4 units of sugar. Okay. And what else do I need to specify for the realistic business? What other constraints do I have?
Like how much the ingredients cost?
Right, maybe, or how much, what is the kind of your budget of like as a baker, you're gonna buy a certain amount of sugar and flour, right? So we can hide the money by saying that I have a maximum amount of flour that I can use, right? And that's how I kind of spend my money, right? So that's my budget constraint. So my budget is, let's say, 4 units of flour and 10 units of sugar. Okay, right? That's my whole problem. And now the question is, like, how many cakes and how many cookies should I make to maximize profit. Okay, so that's the problem, right? Okay, is the problem clear? This is like a standard. This is what this is what happens, I guess, in macroeconomics. A lot of it. Like if you've done a macroeconomics course, the central problem is profit maximization under constraints. Like this is economics, right? Kind of you have constrained resources. How do you make choices? And I think some of the pioneers of linear programming won Nobel Prize in economics just because this is such an important problem. That if you can solve linear programs efficiently, you actually solve a lot of problems in economics. Okay, so how can we formulate this problem? So our decision is we need to choose the number of cakes and number of cookies, right? So we can like assign variables to them, right? So I can say that like I want to make, let's say, x1 cakes and x2 cookies, right? That's my decision variable, and I need to kind of write a program somehow that gives me the best value for x1 and x2 using the constraints and the objective that we have, right? So this is going to be an optimization problem, so we can try to formulate it as an optimization problem. For the optimization problem, I first need to specify what is my objective, right? And my objective is going to be maximize the profit. And we can formulate that easily from the description, right? We've seen that one cake I can sell for $5 and one cookie I can sell for $2. So if I make x1 cakes, then from cake I make 5 x1 profit, and from cookies I make twice x2 profit. And then I add them together, that's my total profit. Right? So my objective is going to be 5x1 plus 2x2, and I want to maximize that. Now, I want to maximize, but I also need to make sure that I'm not violating any constraints. So what are my constraints? My constraints are the total amount of flour and sugar I have, right? So the objective is this, and then we have the constraints. What are the constraints? Basically, I have two constraints. One is how much total flour I have and how much total sugar I have, right? And we specify that I have x1, I'm going to try to make x1 cakes and x2 cookies. So now if I make x1 cakes, how much flour do I need?
Need 2x1.
2x1 units of flour. And then for the cookie, I need 1 times x2 unit of flour. So I add them up, and that cannot exceed 4, because that's my total number of flours that I can have. So 2x1 plus x2 must be less than or equal to 4. That's my first constraint. Okay. So 2x1 plus x2 less than or equal to 4, and that's the flour constraint, right? And the other one is sugars. So if I make x1 cakes, I need 3x1 sugar, and for the cookies I need 4x2 sugar. I add them up, that should be less than 10, right? So 3x1 plus 4x2 is less than or equal to 10. 3x1 plus 4x2 less than or equal to 10. That's my sugar constraint, right? Okay, and now that's basically most of the formulation. Now, are there any other constraints that we should impose on this problem, or x1 and x2?
They should be positive.
They should be at least 0. It doesn't make, there is no physical interpretation of a negative value here, right? So we also need to say that x1, x2, they're then 0, right? And now this whole thing is an example of a linear program. Okay? Why is it called linear?
Because it's a bunch of equations.
Yeah, but the equations have a special form. They are all, you have variables, and the objective is a linear combination of the variables, right? What is a nonlinear, what would be a nonlinear objective or nonlinear constraint?
X1 was squared for some reason.
X1 or so squared, or you have exponential or log or some other nonlinear function. But this is nothing like that. All the variables are used in a linear fashion. And similarly, the objectives are also a linear constant because there is no power or exponent or log or any other nonlinearity here, right? So everything is linear, which is why it's called a linear program. Okay. So in general, you can write a more general form of a linear program. And the general form would look like this. You can say we have C1 x1 plus C2 x2 Cn xn, right? You maximize this, and now in this general form you have n variables, right? And then you can have a bunch of constraints. So you can have a11 x1 plus a12 x2 plus a1n xn less than or equal to b1. am1 x1 am2 x2 plus amn less than or equal to bm. Okay, and then x1 x2 xn all get equal to 0. Okay, so in this case you have, again, this is a linear objective function, and all these constants are linear just because there is no power or nonlinear down here. And this is usually called standard form, right? It's standard because it's a maximization problem, and all the constants are linear, and these are less than or equal to constraints, and all the variables have to be at least 0. So that's known as a standard form of a linear program. And we'll see a bit later, if you have a what is called a non-standard form, you can always convert it into a standard form. Okay? So this is a linear program, and let's kind of think about. So let's kind of try to think about this problem graphically. Like if I try to, so for example, let's say let's say you're thinking about basic geometry, right? You have two lines, right? So if an equation of a line in a 2D plane is a linear equation, right? And then if you have two lines, right, when they intersect, the way you can solve them is you solve the simultaneous system of equations, right? And then you find a single point, and that's your solution, right? But if they are parallel, right, then there should not be any solution, right? So that's the basic systems of equations. Now, let's kind of rewrite our program. Just kind of, it's 5x2. It's going to make some space here. So it was 5x1. Was it 2x2? What was the first constraint? 2x1 plus x2 less than or equal to 4. And the second one was, what was the second one? I think 3x1 plus 4x2 less than or equal to 10. x1, x2 greater or equal to 0. Okay, and now let's just try to plot these on a two-dimensional plane, right? So this will be my x1 axis and this is my x2 axis, right? And now, and then this is the point 0, 0, right? And now, first of all, these constraints, x1 means to equal to 0, that tells us that all the like feasible, so this is any x1 and x2 that satisfy a particular constraint are called feasible points, right? So any feasible x1, x2, they all lie on this upper right quadrant, right? There won't be anything here because this is where there is at least one thing that is negative, right? So this tells us at first that this is the only region we care about. And then these constraints are going to further narrow down my space of feasible solutions, right? What is feasible for this problem? Okay, so what do we have to do? Basically, we have to kind of take each line of these equations, kind of see what is the constraint look like in this region, right? So what is the first one? The first one is 2x1 plus x2. Let's think of the 2x1 plus x2 equal to 4. How would I draw that? So if I think of x2, if I think of x2 to be 0, right? That is x2 0 means you're on this plane, on this line. And then x2 0 means 2x1 is less than or equal to 4, or x1 must be less than 2, right? So in that case, at the boundary, you will have the point x2 0 and x1 2, right? So that constraint should go through this line. So let me write this. So this is the point 0, 2, right? So that equation 2x1 plus x2 equal to 4, that needs to pass through this point. And the other point is, let's say I put x1 equal to 0, right? And in that case, x2 is going to be equal to 4. So the other point it goes through is this one, right? This is 0, sorry, this is 2, 0, and this is 0, 4. So then we have this line here, right? And now we have to be, now this less than or equal to means that we need to choose either this side or this side of this equation, of this line, right? And the way to kind of figure that out is you kind of figure out where does the 0, 0 point lie in comparison to this line, right? If you think of it, if you think of x1 and x2 and put 0 there, you get 0 which is less than or equal to 4, right? So that means that your 0, 0, if I put x1 equal to 0 and x2 equal to 0, that satisfies that constraint. So 0, 0 must be in the feasible region. And then if you choose this part, then 0, 0 is not there. So you can only choose this part. So that means that this equation says that all my points must lie on this side. And then we also have to be on top of this one and on top of this one. So right now, this part is my current feasible region. Okay?
You're saying that 0, 0 is a potential point that should be visible, so therefore it has to be included in your area.
So let me explain again. So every constraint gives us what is called a feasible hyperplane.
Okay.
Of where are the feasible points, right? So x1 greater or equal to 0 and x2 greater or equal to tell us that I need to be pointing in this direction. These are my only feasible regions, right? And then compared to this line, I basically am dividing it into two parts, this part and this part, and I want to find out which part is feasible.
Yeah.
To do that, I use 0, 0 as a test point. And I test whether 0, 0 does 0, 0 satisfy this equation?
Yeah.
So it does. That means 0, 0, if I choose a region for the constraint, 0, 0 must be in that region. So that's why this part is valid for this constraint, not this part. So I would notate that by saying that, like, this part is feasible. So now I already have a kind of small triangular region based on these three constraints, and now I'm going to inject this constraint also, right? So I do the same thing. So if I put x2 equal to 0, then I have 3x1 less than equal to 10, so that's about 3.3. So that means 3.30 is there. So 3.3 should be something like 1, 2, 3, no, yes, 1, 2, 3 somewhere here. So that's 10 by 3 and 0. And the other one is if I put x1 equal to 0, then 4x2 less than 10, so x less than 5 by 2, 2.5. So that's about, I think, about this region. So this is 0, 2.5, this one and this one. And now I'm going to draw another line like this, right? So that's my second constraint, the last constraint. And again, I do the same thing. I check where does 0, 0 lie here. So if I put 0 here, 0 here, I get 0, and this is less than 10. So 0 is part of the feasible region for this line also. So that means, again, even for this one, I have to think of this part as the feasible region. Right? And now I have all these constraints, and all these constraints have to be satisfied at the same time, which means that my total feasible region is going to be this part. Okay, that's my feasible region. Because if you go here, then at least one constraint is not satisfied. You can't go here or here. You also can't go here because there is one constraint on the other side. So this is your region, and this is kind of like in 2D it's a polygon, and in higher dimension it becomes what is known as polyhedra. But the thing to know is this is like a regular shape, and now our goal is to, like, in this entire region, find out at which point do I have the maximum profit. Okay. There are a few things to note here. One is that we have these so-called kind of corner vertices, right? We have like 1, 2, 3, 4 corner vertices in this feasible region, and there is a theory that tells us that one of these is going to be optimal. So that's kind of the beauty of linear programming, and the simplex algorithm utilizes this idea that only on these corner points can you have a actually maximize the profit or maximize the optimal function.
Point of intersection between constraints.
Exactly, and that becomes the vertex of the polygon or polyhedra. So you can see that you actually have a faster algorithm, because if you have to look in the entire polygon, you have like an extremely large number of infinite number of points. And that's going to be very difficult to solve. Now only you have to search and iterate through these points, and then you find a good solution, right? And simplex is about like starting with one of these points and of moving to another one where you have a local improvement, and that's how the algorithm works. But that's the basic idea, right? And now we can also actually visually see what is going to be the optimal solution here. And the way to do that is we look at the vector, we look at the objective function 5, which has the coefficients 5 and 2, right? And then we just form a vector of that, right? What does this vector look like? So, for example, if you go 1, 2, 3, 4, 5 here, and then about 2 here, I think something like this, and then this becomes your vector. Kind of this represents kind of 5x1 plus 2x2, the direction of that, right? And what you do is that basically you take this line. This line represents a vector, basically the vector 5, 2, right? And this represents kind of the perpendicular. So this is basically 5x1 plus 2x, and you have a normal to that. That represents the direction of a normal here. And what you kind of do is that you take this vector and you kind of think of like a normal to that, right? And then this means that as you move this further in this way, you get better and better values for this objective function, right? And now you keep moving and you see that what is the vertex that you can actually cover here, right? So initially you can only cover the 0, 0 point, but then you kind of come here, and then you kind of come here, and then you kind of come here, right? And then you can, I know this picture is kind of very messy, but basically this point is the maximum you can move in the normal direction, and that's the kind of the point where you have the maximum objective function. Okay?
I don't quite understand. It has to capture all the points underneath the normal?
So we know that we will find the best solution in one of these corner points.
Right.
So as you are moving this normal line, you see what are the points that you can actually intersect with that normal plane.
Okay.
Right? So you first come here, right? And then you have this point, right? The value at this point and the value at this point, if you compare them, this is a bit higher value because the normal is moving in this direction and you have better over there. Similarly, this is hard to see, but the normal is such that this, in this normal direction, this is further away compared to this one.
Okay, I got it.
So compared to this, you also have better solution here. But as you go here, this is now no longer feasible. This is outside the region, so you don't consider. So this is the maximum point, and that's your optimal solution. And the simplex method, that is an algorithm for this, is kind of a numerical way of actually iterating through the vertices and finding the optimal value. Right? So in this case, this is going to be your optimal. Okay. So that's kind of like, I didn't go through too much of this. For our purposes, what's important is to understand how we model a problem as a linear program. And we're going to assume that there is an efficient algorithm for solving it, right? So in this class, we're not going to look at those algorithms, but we know that exists, right? And we'll use that for our purposes. Okay?
And the vector is of infinite length, the 5x1 plus x2.
Yeah, you can go as farther as you want. So basically, what you care about is this vector, and you take the normal of the vector.
Right.
And the normal represents all the points where you have, so these are what are called control lines. These are the points, once you have a particular line, that's where you have the same value for all the points in your system, in terms of objective function. Right?
Okay.
And then as you move forward, you increase the objective value.
And why do we use the normal? Or to identify the best? Or is this going to be covered later?
No, I'm not going to cover it later, but the idea of a normal is, so the way you can think about this is like, so maybe another example to make this clear is, this is typically like if you have like an equation like x squared plus y squared equal to like k, right? This represents where all the values are like 0.
Yeah.
And then these represent where your k is increasing. But every point on this one has the same value of k.
Yeah.
So they are kind of, and this is called the control line, where your equation has the same value.
Sure.
Similarly, the idea here is that you have these lines, right? And then for this one, this represents kind of the direction of moving, of increasing objective values. If your objective is, for example, x squared plus y squared, right? Similarly, if you think about this, right, if you have like something like 5, 3, right? So, okay, let me kind of try to explain this a bit better. So basically, your objective, let's say, is ax plus by, right? And this is a line, right? And this, let's say, this line represents ax plus by equal to 0.
Yeah.
Okay, and then as we are moving in this direction, let's say I have the next. Now I want to see where does the line ax plus by equal to 1 lie? Where does that lie? That if that lies here, right? Because these two lines have to be parallel, right?
Right.
Do you agree with that? And then this one is going to be ax plus by equal to 2.
Okay.
But if you look at these lines, you can now infer that as I move normally across this line, my objective is increasing.
Yeah.
And this is the objective.
But
That's all I'm saying.
You don't have to make it a normal. You can make it under 30 degrees instead of perpendicular. I'm wondering why you picked the normal of the
It
spectrum.
has to be normal.
Why? I don't understand. Why is that the optimal one? Why couldn't it be under 30 degrees?
How would you do 30 degree?
Just make it slanted like this instead of like this. You make it under a different degree. I could draw it on the board. I understand intuitively. I guess it kind of makes
Okay.
sense. Just I feel like
It has to be normal, so maybe
Okay.
we can take it offline because there is some geometry here, but this amount of intuition should be enough for us to understand this. But we can go more deep mathematics. But it's when you're looking at direction of increasing objective function, it is always the normal, right? There's a lot of reason for that, but I'll probably have to give you some references to kind of convince you. Okay. But that's kind of the idea. And so now, if you agree that the normal is so the intuition is that you have all these parallel planes which represent increasing by the objective, and the direction which is increasing, it tells you which is the direction of where the objective is going, right? And then if you look back at the picture here, right? These red lines, these represent the value of 5x1 plus 2x2 for different values. And this says that as you are going in this direction, that value is increasing. And then you kind of see that where does it intersect, that objective, where does it intersect maximally with the polygon, and that's where we have the maximum objective function value. Okay. Right? So we looked at a general form of a linear program. We kind of looked at an example in a general form. We saw the general form can have like n variables and n constraints, right? So I can actually write it in a compact form, right? So So this is my general form, right? Now, so this is where we can think about matrices. Right? Do you see a matrix here? Right? What is the matrix?
Equation.
You just take all the AI coefficients and you can put them in a matrix, right? And what would that equation look like? First, kind of let's look at the objective. The objective function I can write in a compact form, right? So tell me if this makes sense to you. I'm going to say that the objective function is basically a vector C transpose times X transpose, where X is basically X1. I just put all the X variables in a vector, right? And the C, I put them C1, C2, Cn. I put them in another vector. And then this is basically the dot product between those two vectors, right? So I can represent the omni function as a dot product. And now I have n constraints. Each constraint has the same n variables, right? And I can just pick out all these a coefficients and kind of just put them all together in a matrix, right? So what would that look like? I can do A11, A12, A1n, A21, A22, A2n, A M1, M2, A, Mn, right? And then I'm going to put them all in a matrix, right? And now I want to actually formulate this as a matrix equation. I need to have this matrix, and if I take this matrix and multiply it with a certain vector, that result should be less than another vector, right? And the way this would look like is that this is going to be my same x vector, right? Okay. If I do this, then you know that the way I would compute this, I would take this and take this row and column and do the dot product, and that gives me my first value, which is exactly this one. And similarly, I can do it for all the rows, and I get them. And then once I do that, I get m numbers, right? And those represent these m linear combinations, and they are all component-wise less than the b's. So I can take all the b's and put them in another vector and say that this is less than or equal to that b vector. Okay.
But you can't perform this operation unless n is equal to n. No, your rows are the same as your other rows.
Mm-hmm. The number of constraints and the number of variables will have to be the same for the linear program. Depending on it, it might be that unless you're careful, you might have like an invalid physical region, right? No, there are no physical regions based on the constraints. Or you can have an unbounded region. That's possible. If you're lucky, you will have a nice polygon, right? So this is the number of rows is the number of constraints, and the number of columns is the number of variables, right? And now this I can call a matrix, and this is my x vector, this is my b vector. So basically, if I call this the matrix A, and this is x, and this is a b, my constraint is going to be matrix AX less than or equal to b. And then I can also write x greater than or equal to 0. That means x is a vector where all the components are non-negative. That's what I represent by this. Okay. So now with that, I have a very compact way of writing a linear program. Right. So my objective is I just want to maximize this dot product subject to this matrix equation and the positive constraint. Okay. So now let's talk about a few things. So we said that form, so we have this form, right? This is called kind of the standard form, right? So when we have a standard form, it's kind of the canonical form of a linear program. But what happens if you want to solve, for example, let's say your problem is such that you're trying to minimize cost, some sort of cost, right? Instead of profit, you want to minimize cost. So how if you have a minimization problem, then it's no longer a standard form, right? But there is a way to translate your minimization problem to a maximization problem, right? So what do you think we can do if you have a minimization problem? How can we translate this to a maximization problem?
Something involving dividing it by a negative that should flip the sign.
Exactly. So basically, if your objective is that, let's say, minimize, let's say, C transpose X, right? This is the same as maximizing minus, C transpose X, or maximizing C transpose minus X, right? So if you just flip the sign, you get a maximization problem, right? So basically what you would do is basically maybe your X variables should keep the same, but just take the C coefficients and kind of just negate them. And that would be the minimization problem. Okay? And now, so if I have minimization, I can translate back to maximization and then I'm back to the standard form. The reason I'm emphasizing the standard form is because if I have a standard form, I can do a lot of operations efficiently. And I want to say that this is a very general form that all possible linear programs can be compactly represented in the standard form, right? And that's going to make our life easier when we actually have to talk about dual programs, right? And that will come up a bit later. The other thing is that, let's say I have a constant such as, let's say, ax plus by greater or equal to 0, right? Again, that's not the standard form. What would you do?
You would make A and B negative.
Right, you can do the same
by
trick.
negative 1.
So maybe this is not A, but maybe this is like, let's say, D, right? Then you can just negate everything, and then you have like minus A x plus minus B y less than equal to minus D. And then you again have the standard form, right? Let's say, what about, so then we are again we are not losing anything by just considering the standard form, right? Because even the other type of constraint, I can do the same thing. And now what about if I have a constraint like this, ax plus by equal to D, what would you do?
Isn't that a valid constraint?
It is a valid constraint. You can have a, because it's a linear program,
Oh,
but it's not a standard form. The standard form is that this has to be less than a. What would you do here? When I say A is equal to B, right? Another way of saying that A is less than equal to B and A is less than equal to B. If I have both of these constants, A has to be equal to B. So I can break this into two equivalent constants. So this would be the same as, right, and then ax plus b equal to d. Basically, you take one constant and replace it by two constraints. That's fine. The standard form doesn't say how many constants you can have.
Right.
And then this is already correct, and this will be just the previous negative. Okay. So again, we are really general. So this is going to be minus. Basically,
Russian always feel like I'm tricking somebody.
right, and then you can do less than, right? Okay. Now, the other thing that we have is that, like, for example, if my variables are x1, x2, I want them to be always positive, right? And if you want to remove this constraint, what can we do? Let's say I wanted a linear program where I have all the other things as before, but I don't want to restrict my variables to be positive. I can also want them to be negative, right? So I would say that, like, I just want x1 or x2 just to be any real number, right? Then how do I make it standard form?
Well, if it wasn't any real number, and it was some type of capacity on the negative number, you could shift all your equations by that amount.
Right. if you shift anything, then you're changing your feasible region. You're kind of the geometry is
Right.
changing, so that may be a good idea. So here there is a very nice trick. Is if I take, let's say I have two variables x1 and x2, and I don't want to restrict them to be positive. What I can do is that I can write x1 as x1 dash minus x1 double dash. And then I impose that x1 dash and x1 double dash, they both have to be equal to 0. And now I take my program and replace x1 with these two variables. And they have to be positive. But because I have a positive variable minus another positive variable, this together covers all values for x1. So basically I'm going to take every variable that has to be arbitrary and replace that with two positive variables. And then I am back in the same form. Right?
Yep.
So every variable that you need this, you just replace it with two variables and express them as the difference of those two positive variables. And then after all this, we are again back in the standard form. Okay? So the standard form is very general, and from now on we can just always deal with the standard form. And the idea, or at least the way I think about linear programming is, even if I have a linear program in a non-standard form, I would always try to translate it to a standard form, because then all the calculations and analysis becomes very easy, and you just have to think about one case and you're done. Right? So that's kind of the idea here. All right. So before we kind of take a 5-minute break, I want to just give, like, why are we talking about linear program? What is the connection, right? And I already mentioned that one big connection is connection with max flow problem, right? So now if you look back at the max flow algorithm, it's exactly a linear program, right? So what was the max flow problem? Right? So what did you have? You have this graph, right? We have all these capacities. A source and a T, right? All the edges have capacities, and then you have these flow constraints where the flow that goes through here, it must be equally split on these two paths, right? So if there is no flow, you cannot constantly flow in any of these points. Just only the source can have a positive net flow going out, and the terminal can have flow going in. But every other place there is no flow that stays in that node, right? So the way we write this is that the maximum moment is basically taking the total flow out of the source and maximizing that, right? So now what are my variables here for the max flow problem? So I'm trying to write this as an LP. What would be the variables? What are we trying to optimize? The variables?
Your paths.
What is the solution of the flow?
It's your max flow.
Max flow is the solution, but max flow is the optimal value,
Yeah.
but there is a solution,
It's your
an instance of a solution.
your cut solution.
No. For every edge,
Right.
I'm giving it a flow value.
Right.
So that is kind of the solution. And we are trying to find the flow value that maximize the total flow out of the source. Right? But if you think of, like, for example, if you think of shortest path, there is an optimal shortest path, which is the value is kind of the length of the shortest path, but your solution is actually a physical path. You have to define that path, and that's the optimal path that has the value of a shortest path solution. Similarly here, the max flow value is the sum of the flows out of this source vertex. But the solution to the flow problem is an assignment of a flow value to every edge.
Oh,
Right? That's what I mean. So then for every edge, I have a flow variable, which is what I'm trying to find out or solve for. Right? When you finish your Ford-Fulkerson or Denise algorithm, right? At the end, your solution is an assignment of a flow to every edge. And we find the assignment such that the sum of the flows out of the source is maximum. Right? That's what I'm trying to solve here. But the variables here are basically the variables are like FUV for UV in the graph, right? For all UV in the graph. That's my solution, right? And then, so those are my variables. So this is like my x1, x2 in my linear program. And now, let's maybe just use a toy example just to kind of make it clear. Yes, T, right? And let's say I just, because it's a small example, I can just put in the edge name. So this is E1, let's say. Or let's just use S, this is X, Y, right? So I have the edges SX, XY, SY, XT, and YT, right? And then I want to maximize, I just want to maximize the flow across this edge and this edge, so two values. The sum of that has to be maximized, right? So then I have a maximize FSX plus FSY. Now is this, if my variables, so my variables are all the flow values. So this is a variable, this is a variable. I'm summing them up and making that the objective function. So is this a linear function in the variables?
So linear function. It's not a function, it's not. Second time.
Is the objective function linear? So so if you look back at the cake example, I had something like 5x1 plus 2x2, that was my objective,
Yeah.
right? So we said that this was linear in x1 and x2.
Yeah.
So here I have variables fsx and fsy, and I'm adding them. So you can think of that I have a coefficient of 1 in front of all of them.
Yeah.
So it's still a linear function.
Oh.
Right? And what are the constraints? So I would only have two constraints, right, here. Two flow constraints. One is for this node and one is for this node, right? So for the first, for the node X, the incoming flow is F Sx, right? That's the only incoming flow. And the outgoing flow is Fxt plus Fxy.
Be less than or equal
The flow has to be equal. That's flow conservation, right?
to. Okay. That's why it has to be equal. Can't you?
But this is, you already done, you already did
Yeah.
this beginning subject number. This is flow conservation. The flow that goes in this one needs to be equal to flow that goes out
Oh,
of
yeah,
this node.
sorry.
These are the flow conservation constraints.
Yes.
I think you're thinking about the capacity constraint.
Yes, yes.
That's what we're counting, right? So these are the flow constraints. And the other one is for the node Y. So in node Y, we get F, Sy goes in, and what goes out is F, Yt. Oh, sorry. Two things go in, right? At Y, we have Fsy going in and Fxy going in, right? Plus Fxy, and that has to be equal to Fyt. So these are the flow constraints, right? And again, these are linear because I'm using these flow variables and everything has a coefficient 1. And this is equal, but it's fine. You can transform it to the less than equal to constraint using the tricks and the right? So again, these are linear constraints. And then what else do we have here? What other constraint would we have? That for every edge, right? For example, if f of x must be less than or equal to the capacity of that edge, right? So f sy must be equal to the capacity of that edge, and then f x y less than or equal to capacity of x y, if x2 is equal to c of x2, and then f y2 less than or equal to c of y, right? And again, these are already in the standard form, right? But when all these constraints are linear, downstream is linear, and then there is two variables which you want to be positive, right? So if we always go to 0, and then this all is a linear program, right? And now if you solve this linear program, right, you should get the solution to the next problem, right? So we actually don't even need to solve the first time coordinates away from those complicated algorithms. Maybe it's not complicated, but if you think about it, like you cannot discover algorithms. You put as the problem is in an LP, and now once I know it's in LP, what can I do? I can just throw it into a web solver, like simplex somewhere. We will start an auto solver for that, and then we are done. Or we can just say that it is solver because I have an LP, I just need to solve that in a program. So we generate much more general solution, right? So in some sense, a lot of common problems that you encounter in graphs or in a test, if you can find the information, you already know that it's the problem that solves the problem. Okay. All right. So let's maybe take 5-minute break and then we'll come back.
So I just submitted this from your point. Yeah.
I cannot see. We are looking for the structure of these algorithm, but your solution would be the same, right? If you, then I would tell you we need to do a simple algorithm. It is much more complex than that. Then we will also be looking at other stuff. Try to call the dots and flex. Well, I don't see it in library where you can call like flow.solve and solve a flow problem, right? Oh, so maybe we can define.
Just I know it's a flow flex.
Yeah, we can do simple as that. I mean, all you do is you have solved a lot of problems for LPs where you simply write them in constraints and specify the variables and then you can solve it for you. So you can take a open source solver called GLPK, G linear programming kit. All you do is specify these constraints, quantity functions and variables, and release a solve and you get a solution.
Systems of equations with just nullify all the 3 seconds of equation.
Yeah.
Just look at everything close to the equation.
Exactly. Let's just try. So now, for one example, we see that. So now that we get any graph, right, any closed problem, you can follow visibility, right? So you can have a general graph, let's say a graph which has this kind of capacity constraint, right? You can define FUV to be positive numbers for every edge. Right? And with this we can formulate the maximum problem. Right? So what is going to be done with the general objective function for a graph? What I'm going to maximize is going to be a sum over some k variables. And the flow goes out of the source. So you need S is, let's say, x, where let's say Sx belongs to B. That represents all the edges where S is the first vertex, right? And then what are the Cauchy constraints? So the constraint is called as such that S dot T. So the flow conservation, so let's first write down the capacity constraint. The capacity constraint is that my flow at any edge UT is less than or equal to my capacity edge, right? For all UV in the graph. That's my capacity constraint. I have one capacity constraint for every edge in my graph. And then the flow conservation happens for every vertex except the source and the sink, right? So for all vertex u that is not equal to the source vertex the sink vertex, right? What happens is I have this vertex u, I have a bunch of incoming flows and a bunch of outgoing flows, right? The incoming flows will have u as the second vertex in the flow parameter, and the outgoing one in the u as the first vertex, right? So I can write this like this, that summation of I can write like this, that x comma u then edge, right? I think I said it, I said it wrong, right? So the incoming ones will have u as the second edge, right? Okay. So x means the incoming flows. So those flows, all of them should sum up, right, to be equal to the outgoing ones. The outgoing ones are where u of x is in the graph, to the edge, therefore ux. Okay? So that's the conservation constraint, right? And this is assuming there are no incoming in x and no outgoing in this one. And then this is the general form of the macro problem. It's a linear program. You can just take this over and do that. Okay? So that's an example of a very nice application of linear programming to our algorithms. Right? And we'll see much more applications today, hopefully today and also in the last class. Okay. So next, let's talk briefly about so linear programming. So we saw how we can model an optimization problem in linear program. This standard complex kind of form, right? But when it comes to math, we have to not solve for that. So how do we solve it? There are very famous algorithms for solving this using an algorithm, right? Once you have the specification of objective and constraint and variables, you have a problem to solve, you need an algorithm to solve, right? And there are algorithms, right? And So linear programming is in P. It's not a R problem. But it's a very huge key algorithm because the algorithm that is actually mathematically proven to be polynomial in the worst case is a very complex algorithm. So let's kind of just like let's talk about them. So LP algorithms. So these algorithms that actually that are kind of some of these are built inside LP solvers. Like they call these algorithms to solve problems, right? So there are three well-known algorithms. The first one is called simplex, and this is by far the most popular algorithm, simplex. It was discovered by Danzig, right? So this is going to be extremely fast in practice. But the worst case, just like Quicksilver in the worst case is quadratic. In this case, the worst case is exponential. Right? Worst case, it can be exponential time. But why is it used so much? Because it's used so much because whenever you think about simplex, you think about the input to the problem is a unit program. Almost all linear programs that you find in practice or on average, for those problems, simplex runs extremely fast. There are only a few extremely intricate corner cases where you get exponential output. But mathematically, we have to say that this algorithm is not polynomial because our measure of complexity is that for all such inputs, it has to be polynomial. But that is not simplex. But it is still used in practice because, as I say, like in some sense, 99.999% of realistic inputs, simplex is reasonably fast. Right? So it's really fast in practice. And then there is also a beautiful mathematical theory around the average case performance of simplex. Right? And someone got a lot of prizes for that. It's called, I forget its name, but I'll share an article on it. But, then simplex, then LP is actually in P, and the reason for that is this algorithm called ellipsoid. Ellipsoid algorithm, and this proves that this problem is actually mathematically equal, right? Which means that even for in worst case scenario where simplex is exponential, ellipsoid algorithm is non-linear. So in Q it is very fast. So in Q it's fast. But it's really complex. So when you say complex, I mean like for example, using a Google primary search, much of the easy class, Google algorithm. And it is like such a complex algorithm, you say that it's impossible. In fact, in some sense, there are some beautiful complexities in ellipsoid where, in some sense, you have to think about representing individual number of constraints in polynomial space. Right? There are some complexities like that. And those are not, when you think about actually writing this program, it's really hard to write it down. But a simplex is really just to approximately right? The other type of algorithm, which is very popular, so ellipsoid was developed by a Russian mathematician, I'm not sure I'm pronouncing it right, but the third one are called interior point methods. And this is kind of a breakthrough. The interior point was a breakthrough. And this was done by Karl Marker. in my own labs. And this is called like both fast in theory and practice. Right? But again, there are some products where this can be very slow. But in general, what in theory and practice is very fast. And the idea of the interior point method is basically, if you recall, what we have, the LP feasibility looks something like this. You kind of have this kind of polygonal region, right? And the simplex, what it does, it just searches through these corners. Okay? So it's kind of iterating through these corners. And now for this example, it's like 6 words and not very simple. But realistic linear programs would have, if you look at the possibility, millions and millions of these services, right? So it's not easy to kind of iterate that. What internet one does is basically saying that I have to really utilize the space inside. You search here. So kind of somehow, instead of moving from these discrete points, it kind of goes through the continuous space to the clusters, the cluster nodes. That's very interesting when we like doing something. I'm not going to. And these are in industrial standpoints over these are the most important.
Yeah, when there was a conflict of the intersections, there would be a lot of further constraint.
Right. Every pair of constraints you have kind of, you do the intersection of the constraints.
Yeah.
So now, the number of instruments is at least quadratic.
Yeah.
So if you have linear possibilities like maybe for 9 plus 9 or something, right? Or then it's 6 plus 6 constraints, right? So this can actually go a bit fast. Okay. So that's something that, and again, like if you recall in one class, I kind of showed you the list of the greatest algorithms of the last century, and you saw that what the effective was there, and other one was actually sequence. Okay, so the LP solver, these are like breakthroughs in the side. And the field of problems really depends a lot on solving the problems. Because this is the list of key problems is what comes up with microeconomics. And multiple economists won Nobel Prize for contributing to linear programming. Okay. The ellipsoid, like, it's mostly a theoretical algorithm. We say we use ellipsoid to prove the complex systems. Okay. Or kind of showing you that polynomial algorithm for some other problem. Right? So it's not really used like this.
You should understand why it's
So what I said is that the way to kind of compactly represent a large number of constraints, like in theory it's possible, but you actually have to write code for it. That becomes really hard. So there are a lot of these constraints. There are ideas like these in powerful local abstraction inside the algorithm. Oh, in theory, like it's kind of like an addressing or something like that. Like you have a space and you kind of need this oracle point that kind of somehow basically what it does is we have so what you know linear program is so in the linear program our objective is to find the best arbitrary program. And what we are trying to find the point inside the physical region that maximizes probability. There is an argument, mathematical argument says that if you can just take an arbitrary point in the space and just be able to check whether this point lies inside the physical region or not, that discrete problem is equivalent to finding the maximum probability. So for solving LP, complex actually used to solve a feasibility check problem. You take any x in like three-dimensional space, and you just addition problems and get this x inside the feasibility or not. If you can solve it for minimum time, you have a problem. So the user algorithm is basically a very fast check that is very fast. And what it does is kind of it basically looks at the space and has a smart way of taking operation, cutting out the space in half with a binary search first. And then typically we have one of the physical part. Right? That's something that what happens in the responsibilities is always coming from the starters. And engineering is kind of close related to because it also seems to be in space. But initially it's about like how we actually find these players to kind of cut down this complexity in a large chunk to do this fast. Right? That's kind of the idea here. But it's a very complicated idea. Whenever I read it, I never remember it. I have to read it again. And for practical purposes, like even in my work, I work with optimization solvers, but maybe just use the solver and never think about it side for examples. Okay. So that's all we're going to about linear programming like algorithms. And I'm going to look at these algorithms. But now I want to talk about a very like elegant and very important idea in linear programming, which is the idea of duality. Right? In some sense, every linear program is a dual program. Right? You can always have a dual program. And there is a connection between the main problem program and the dual program, which you can utilize to solve efficiently, but also design algorithms. Right? So what is the dual program? Let's kind of think about it. Okay. So let's use an example. It's specifically the bakery example. So I want to maximize, let's say, 3x1 plus x2 subject to I might be changing the numbers, but in spirit it's the same problem. Okay. So let's think about this program. So when you first have a linear program in standard form, it's usually called a primer program. Primer because when you have a program, you say primer program. Right? But this program is in our primer program. It's called a primer program. Right? This is called the primer LP. Okay. Now let's think about this and what are we trying to do? So we are trying to basically we're trying to find the best value for the objective function. Okay? And now it's possible that you might be unlucky, and then the max is going to unbounded. You have this such a weird space. And what could happen, for example, you might end up with a feasible region like this, right? There's nothing that prevents from this happening. And then your objective normal, right, that is going in this direction. Right? And then this is your feasible region. Everything on this side. So this is basically an unbounded problem, right? If you get the maximum realistic, there is no stopping. So in that case, you will have a solution for this problem. That's unbounded. Now, the motivation for dual is kind of we are trying to find the best value, the maximum value for the objective. The idea of the dual is kind of can we kind of find a bound on this objective function? We find an upper bound, right? So the upper bound is kind of like saying that okay, this is the maximum we can do. So if you can find the idea is that my idea upper bound is going to be an optimal solution. And I can always find a reduced upper bound if I'm trying to improve it. But if I can find some sort of finite bound on the objective function, that will help me narrow down my search space. Right? And now to find a bound, so this is the maximization function, and I can find a bound. What information can I use to kind of try to find the bound?
look at your constraints, because they're
Exactly.
forward.
The constraints are these bounds, right? So for example, we know that the first constraint is bounded by 2 and the second constraint is bounded by 6. So if I kind of somehow use these bounds to bound one function, then I'm in good shape. Right? So the idea is that the idea is to think about, let's use some combination of these two constraints to find the boundary point velocity function. So in general, what I would do is that I can think of, okay, I'm going to somehow multiply this constraint by a variable y1, multiply this by y2, and see if there is a combination, a linear combination of these two constraints that will upper bound my velocity function. And if I can do that, then what happens? So basically, I'm trying to basically like the idea now is that can we find values y1 and y2 such that the linear combination of these constraints dominates the objective function. So such that 3x1 plus 2x2 is bounded by y1 times the first constraint plus y2 times the second constraint. Right? And now, what do we know from the constraint? From here we know that 2x2 plus x2 is less than equal to 2 and y1 is equal to 2y1. Right? So then this is going to be less than equal to 2y1 plus 6y2. Okay? And now, if I can find the valid combination of y1 and y2, which dominates the objective, then I have found upper bound. Right? And now this is an upper bound. The way I can try to narrow this down is if I can find the tightest upper bound. Right? So in this case, we will say that so we know that x1 and x2 is to become all positive. Right? And now if I can find positive y1 and y2, right, such that this is bounded above, which means this bound is from the above, then my goal is going to be trying to find the best possible best values for y1 and y2. Right? So my objective, so basically I want to find the tightest upper bound, the tightest above this one. And how can I make this tighter? In terms of choosing y1 and y2. What would I, so like this, for example, like let's say I somehow find that, let's say this turns out to be like, let's say some value is like 5, and this becomes like 7. Right? This value. But if I want to make it tighter, I try to make this, let's say 6 or 5.5. So I need to kind of tighten our bound. I need to look, I need to find y1 and y2 such that this is as small as possible. So this is like something to minimize. And that's the idea of the dual. The dual is now, so now this is my primary objective function, and this becomes a dual objective function, right, which I am trying to tighten as much as possible. But I still have the dependent constraint here, which is that if I kind of write this down here, if I kind of so let's kind of see what this turns out to be. So this, if I just like write it, kind of break it down, what we have, 3x1 plus 2x2 less than or equal to, right? So I have x1 and x2 here. So let's kind of merge the positions for x1 and x2. So x transpose is going to be 2 by 1 and 3 by 2. Right? So I can write it as 2 by 1 plus 3 by 2 times x1, and then plus for x2 is going to be y1 plus 4 y2 times x2, right? And this will be plus 2y1 plus 6y2, right? So I'm trying to tighten this upper bound, so this is what I'm trying to minimize to match this final objective. But my constraint is that this, I need to maintain this, right? That the coefficient of x1, which is 3, needs to be dominated by this term, for this two value. Right? Similarly, this coefficient 2 needs to be dominated by this term for this two value. Right? So what I can now, so what I have is, I have this expression that I'm trying to get as low as possible. So I need to minimize this as much as possible, but I cannot minimize it beyond a point where these are not running those coefficients. Right? So basically I can now, from my original program, I get this as a new program, which is I want to now minimize 2y1 plus 6y2 subject to these dominating constraints. What are the constraints? The term 2y1 plus 3y2 needs to be greater than equal to 3. Right? Yeah. So such that this is right. 2, 6, 2, 3, 2, 3, 4. Okay. And then the other one is that this will dominate the other value, which is, right? So the other part is y1 plus 4 by 2 must be equal to 2. Okay? And if I, so these constraints ensure that the combination of this combination dominates the final objective. And by minimizing this, I'm trying to squeeze it as much as possible. So if you have optimized models, you can think that this would actually can be exactly where the maximum can go. Right? So we have the primal is trying to move the maximum to the dual is trying to squeeze it down, and when they immediately going to get optimal. That's the kind of data. Right? So basically, if you look here, what you have here, and then these are have to be also positive. And now this program is called the dual. This is called the dual of the original problem. Okay. And now, what is magical is that I look at the dual, I can look out at the primal. I look at the dual and I can write down. So let me write it down for you. I forgot the primal, but I can write it down. What I'm going to do is that in the primal we have coefficients. Right? The primal coefficients go on this side of the constants. So it's 3x1 plus 2x2. So the primal plane is going to be, and now the dual is minimum and the primal is to maximum. So the primal is, I'm going to maximize 3x1 plus 2x2, right? So let's read it off from the dual. You can see that it's equal to the primal used to be a. And then the constraints are basically, we have this matrix of constraints. In the dual, all of them kind of gets transposed. So I can again, I can write down the constraints because my first constraint is having to use 2 and 1 here. So it's going to be such that 2x1 plus x2, and then whatever is here, this is now a bound constant. So this is going to be 2, and then similarly it's going to be 3x1 plus 4x2 is equal to 6, x1, x2 is equal to 0. And that's my prime one. Okay, so let's double check if the primary is correct. It's correct, right? Okay.
So some matrix operation for you with the focus?
It is in matrix. So now, if we think about this, the general form of the primal is maximize C transpose X such that A of X less than equal to B and X is less than equal to 0. Right? What we do is that, so in this case, the way we got from the primal to the dual is for every constraint. So the primal has variables, right? The dual has variables. The dual variables correspond to every primal constraint. So we choose 1 here and 1 here, and those are the variables in the dual program. So Ax is going to be the size of these n constraints. We will have n dual variables, and that we represent by the dual variable is going to be y, which lives in the space of like Rn, right? So basically for every row of X is equal to B, you have a dual variable y. And now the corresponding dual is always going to minimum, right? And it's going to minimize over the vector y, but then what was a constant here that becomes the object here is going to be transpose y. Such that, and what happens here is that this gets transposed, so it's A transpose to the variable y, and what else happens? If you see here, these are nesting constraints, and then what becomes the other constraints. Right? So again here, the same thing is going to happen. This is going to be between 8 and 2, and the objective vector goes to the constraint. C, and then y must be equal to 0. So that's the formula for deriving a dual program from a primal program. Okay, isn't that neat? It's very neat. It's one of the most powerful theories in linear programming. Yeah, that's the idea. Okay, so this kind of is the process of dual makes sense. Now we have a maximalism objective we're trying to bound it from our. And the dual program is just taking a linear combination of the constraints and using it to bound the objective as much as possible. And once you find the best all around, we actually have to have the optimal objective. We have to match up. Okay, that's one idea. And that idea is so let me just write down one thing for your information. Basically, for every primal constraint, you get a dual variable. Every primal variable becomes a dual constraint. Right? Is that clear? Right? So that's kind of the dichotomy. Right? The constant and the variable swap in the primal and the dual. Okay. And now there is this notion of what is known maximize with duality and strong duality. Okay. What does this mean? Let's talk about weak duality first. Like, if let's say I have, if E is a primal AP, if P is, by P I mean the objective function and the constraints, it's a program. If P is a primal AP, and let's say D is the dual, right? So this is the dual possibility. This is the dual that we get from D in the process. And now, the way that says that if, so once we have a primal program, my goal is to find the optimal or maximum value of it. So if the optimal of the primal program exists is finite, right? So we saw that it's possible that it may not and not, right? So we have this open point one, and we have this maximum number right? But if that's not the case, then the primal actually has a bounded maximum value. In that case, the optimal value for the primal program is always going to be upper bounded by the optimal solution to the dual program. Right? That's basically the real duality, and this makes sense, right? The purpose, that is actually the purpose of the dual. The purpose of the dual was to find the upper bound of the primal objective. And then ideally, is not possible. And then ideally, the dual find can minimize the dual objective. But this is always has to be dominating the primal objective. Because that's the purpose of the dual program. Upper bound program. It is, so in this case, I'm saying that equality means that E is a probability and if E is a probability, then E is a dual, and the other condition is that the primal is finite. In that case, this fails. What we say is from project. For that to happen, the dual program minimum also is finite. Okay. So when both of them exist, then we have exact match. But that might not always happen, right? So basically so that's the strong duality. Right? And strong duality says that if both the optimal of the primal and optimal of the dual, if they both exist and are finite, then they must match. Which makes sense. Right? The optimal cannot go beyond the dual objective, and the dual cannot go below the primal objective, because the dual always is higher than the primal. Right? And now, so the proof of strong duality is complex. For example, there is a variant doing that, and a lot of them do, so we will not have one in this class. But the real duality is something that we can quickly show. So I'll try to show that. Okay. So let's kind of prove the okay. For the exam, I will definitely ask you to find the duality of the primal LP in your exam. So please learn this. I will definitely ask the question about this. It's guaranteed. Okay. So the proof of the duality is extremely simple. So let's see what is the primal program. It's maximize C transpose X such that Ax is equal to B, is equal to 0, and the dual is basically minimize A transpose Y such that A transpose Y is equal to C and the Y vector is positive. Okay, and what we need to show, that the primal optimal is upper bounded by the dual optimal. Okay, and now what? So that means we need to show that the optimal of C transpose X is less than the optimal of B transpose Y. Okay, and now how do we prove this? Okay, now let's say that let X be feasible for the primal program, right? It's an infeasible point. That means that X satisfies the primal constraint. So we can say that Ax is less than equal to B, right? And then let Y be feasible for the dual. Okay? So what can we say from that? That means the dual constraint is satisfied for Y. So I can say that A transpose Y is less than equal to C, right? And now from this, if I need a transpose of this, I have to transpose of this one, right? So from here, I can write that A transpose Y transpose is equal to C transpose, and then do you know the rule of transpose? So if I do A B transpose, it's going to be B transpose A transpose. Okay, you can verify that. But then this becomes Y transpose A transpose transpose. If you transpose the matrix first, you get that original matrix. So this is Y transpose A. We are going to C transpose. Okay. And now, what is the primal objective? So from here, I can also say that I just say that C transpose is now less than or equal to Y transpose of A. Okay. My primal objective is to C transpose X, right? That's what I'm trying to maximize. And then C transpose I can replace with this, right? I can say that now C transpose is based on from here. I can say that C transpose X is less than or equal to Y transpose AX, right? And now what about AX? From here, now I can look at here, I take this, I can replace it by less than or equal to B. So now this is less than or equal to Y transpose B. But now what is this quantity? Again, this I can write as B transpose Y. Right? It's the same dot product. But now look back at the dual program. So B transpose Y is exactly the dual here. So what we have is that for any feasible primal objective value, any feasible primal objective value is upper bounded by the dual objective value. Okay? And now, so what we have shown so far is that C transpose X is less than or equal to B transpose Y for X feasible and Y feasible. Okay? But now, that means for, if I just think about Y, for all feasible Y, the primal objective is unbounded like this, but this also goes for the optimal Y. But this is for only feasible Y, so this also goes for the optimal Y. So that means that this is also true that C transpose is less than or equal to the optimal value for B transpose Y, right? And then now if I have this holds for all feasible X in the primal feasible space. That means it also holds for the optimal X. So that means it is also true that the optimal value for for C transpose X to use upper bounding by the optimum value for V transpose Y. Okay, and that's the proof. That when you solve the formula, you find the optimum value, that is always optimum value. Right? And then this practice appears if the dual has a finite. The dual actually has, because this doesn't, this also knows if this becomes infinite or something. Right? So if this also exists, then you actually get equality. This is the strong duality. And that's the requirement report. Right? Strong duality. So that proves the weak duality. And strong duality, which hard to prove, and there is a very modern way of proving it using something like multiplicative weight update algorithm. So originally there was a very complicated proof for this, but there is a modern algorithm proving the strong duality, which is known as the source. Alright. So I think that's it today. In the last class we tried to, so basically this is what we're going to apply to next flow, and then we will actually approximation algorithms, which use linear programs. And that will be the end of the semester.